Get started. It's a great pleasure to introduce Dr. Ruchir Puri as our distinguished speaker for TILOS seminar today. He's the Chief Scientist of IBM Research, IBM Fellow, and Vice President of IBM Corporate Technology. He led IBM Watson as CTO and Chief Architect from 2016 to 19. He's a fellow of IEEE, has been ACM Distinguished Speaker, and a long list of awards apparently. So today he will talk about the exciting topic of engineering the future of software with AI. And welcome. And please take it away. Thank you.
Thanks, Ekan. Appreciate it. So this is a topic, as certainly Grady knows he's on the call, a topic I've felt very passionately about for last 3 years. Way before the current wave of ChatGPT arrived. And since everything in the world is becoming software defined, whether you are doing hardware, you are speccing hardware, you are designing hardware, you are dealing with infrastructure, everything is software defined. So the topic has relevance to everything that we do, whether we do hardware or whether we do software, because to a large extent, VHDL, Verilog, or any other system C or anything else is a software spec as well. So I just wanted to first emphasize, and given a version of this talk in various keynotes at sort of hardware design conferences as well, which is of high relevance to the broader set of design communities. Developers, doesn't matter whether you are purely a software developer or a hardware developer. And I've felt it for a while that there are sort of two major waves that are really sort of percolating across society. Everything is becoming software defined, and the wave of AI. And I felt strongly enough for a while, as I said, that these two waves are going to collide. And I think that collision is in front of us right now. 100 million plus people are experiencing this to a large extent. And I'm going to talk about that and see where we go from there. All right. So I think it'll be obviously fair to say that software has had a major role in our lives. And what I just stated was, I believe that AI will have a major role in software. And Grady and I, as I said, who's on the call, has had these conversations off and on within IBM. And the question that we as computer scientists have wondered for long is, this is interestingly the beginning of the Dartmouth meeting as well. Could we have machines that program themselves? So in other words, can computers program computers? They can sort of automatically repair, automatically program. A very profound question, but over time we've been slowly heading towards those kind of machines. Also, somebody will call it thinking machines as well, actually. So I'm going to keep the thinking part out of it and be more tactical in what we could do or we couldn't do. I think it's also fair to say that there are three major legs to the stool of deep neural networks that has been percolating across in everything that we do from an AI point of view. And obviously they are, I would say, none of it would have happened had it not been because of data. Very large set of data sets arrived. The data was becoming free-flowing. We are literally generating peta and exabytes of data on a regular frequency. And we happened to stumble upon, this wasn't by design, we happened to stumble upon, hey, these are these elements called GPUs. They fit the kind of computations we want to do very well. From a linear algebra point of view, they were designed for something else, and those two were married together, and new algorithmic innovations came together to really give rise to the latest and the greatest of AI that we are witnessing in front of us right now. I think it'll be also fair to say that none of it would have occurred if I were to point out one thing among all of these three, which was critical to us, I would really say it will be in the area of data. I think if I just were to point one sort of significant pivot on where we made significant advances, it will be in the area of a data set that all of us are well familiar with, which moved the ball forward, not just in computer vision, but it had implications on fundamentals of neural network technology, which were then applied to natural language processing, to speech, and other domains as well. And this data set that obviously, as I said, all of us are familiar with, which was started by Fei-Fei Li, who was then at Princeton, now obviously, then later moved in a couple of years after that to Stanford. In 2009, there were 3 million images with 5,000 classifications. And when all said and done, the dust settled, they had 14 million images and 22,000 classifications, which literally fueled the revolution of machine learning with this sort of massively sized data set, which was obviously certainly labeled. Which resulted in a human level ability on a certain level of sort of narrow tasks, I will call it that way. I'm not fond of calling superhuman capabilities, because humans, as humans, we do many things. And we have combined numerous modalities. We walk, we talk, we think. We are observing, and we are reacting, and we are planning. And we do all of that, interestingly, with computational efficiency that is unmatched by any machine on Earth, and will be for a long time. We do this with a brain which is 1,200 centimeter cube and consumes 20 watts of power, and runs on sandwiches, as I'm fond of calling it. Versus what these machines, single GPU consumes 300 watts and takes a lot more than 1,200 centimeter cube, just the card itself, I would say. So before we get too enamored with these machines, I think the name of the game in computing has always been, yes, computing can be done, but it is about the efficiency of computing as well. And we are far away from that superhuman capability. And I just wanted to emphasize that up front on where we are on that journey. But nevertheless, I think on a narrow set of benchmarks, as I just talked about, we certainly have achieved some very impressive benchmarks with respect to what a human labeler might be, or an annotator might be able to do, versus what a machine might be able to do. And there are implications of that to medical imaging and other areas as well, that are percolating again in many interesting use cases. Which, at least from a IBM point of view, as we were looking at, we started on this journey with the Watson Jeopardy, again, a machine purpose-built to play Jeopardy. We expanded it to other applications areas, including conversation and then assistant, in terms of being an assistant in a particular subject matter or having chat. And then finally, more recently in 2019, that actually expanded with the neural network technology and others combined with it to what is now called Project Debater, to be able to debate the best of the debaters in the world in a live debate, and doing very well at the pros and cons of a particular topic. So that's sort of the journey from where we started from, some really significant advances happening, us looking at it from the point of view of pros and cons of a particular topic given to the machine. And then, I would say more recently, obviously, the chat GPT, where you can certainly have a conversation and really get some really interesting things going with the machine. So things have moved significantly forward from 2019, when this Project Debater was done, to now, where the learning is unsupervised with the attention-based transformers and decoders models only, with massively large number of parameters. Things have moved significantly forward from this point onward itself as well. I think while there's been a lot of talk on, at least in the Western world, certainly in the US, on sort of our aging infrastructure, there's certainly been, since the world has become a lot more software defined, And we in the Western world, to a large extent, started on this journey much earlier as well. Our software infrastructure has also become much more aged as well and is in need of modernization. And now I'm trying to phrase sort of what is the motivation behind trying to use AI for software? What are some more key problems through which we can motivate this to say, yes, it really has a significant business case that we can drive things towards, other than obviously the developer efficiency itself, which has a significant business case. But some of the, obviously programming languages, which were some of the earliest ones, one of the well-known ones that many of us are familiar with is COBOL, which was kind of instituted by Cosadel Committee in 1960s, so roughly around 63 years back now. One of the oldest programming languages, still in high demand. In fact, US government instituted a study more recently, and it came across that they actually revised this 220 billion numbers. I don't know how exactly they counted it, but the estimate was that world is running today around 800 billion lines of legacy COBOL code, which is running 94% of the government, the financial institutions, the insurance industry, and other critical transactional infrastructure in the world. So, just to motivate the problem, obviously this came together at the time, sort of at a very strange, actually, time. Some of the alarm bells that started going out, because a lot of government infrastructure and government services are being run with this infrastructure from a transactional capability point of view. Interestingly, during COVID, when everything shut down and the demand for government services went through the roof, it became clear that the systems that were built with some of this infrastructure weren't sort of updated to keep up to react to a massive inflow of demand that came in. Nothing was actually, I would say, designed for that kind of a scenario, because nobody envisioned that scenario from a coronavirus fight point of view. The world was taken by surprise, and so these systems were not ready. And this is interestingly a headline in the newspapers, which you wouldn't think would be a headline typically: COBOL coders needed for coronavirus fight. You wouldn't think COBOL coders and coronavirus fight will be combined in the same sentence. Nevertheless, this was the headline. And the reason for it really was that a lot of people who were really involved in these legacy programming languages have since retired. If you were working at it in 1960s, you certainly are closer to your retirement point by now, if you have not already retired. And closing that sort of legacy programming skills gap was becoming harder and harder. And there is a need for that infrastructure to get modernized as well. This, interestingly, has been one of the things that we've been looking at, and this is one of the articles that I was interviewed for. This is back towards the end of sort of 2020, so roughly around 2 years back or so. Now, on IBM Watson's next challenge, modernizing legacy code, and we've been making sort of good progress towards it, and I'll cover some of it in the discussion that we will have as well. But really, whether it is from a translation point of view, whether it is from taking a what we call a monolithic legacy code. Many of these things are not written in modular way. The business logic is combined right there with the rest of the application as well, more as a flat file many times. That refactoring and restructuring the code into a model, into a modern cloud native era becomes a very significant and a very hard challenge as well. And how could we bring AI to bear for addressing some of that refactoring, some of that modernization? It's not just a translation task, interestingly. It's more than a translation task as well. And that's why it's a significantly harder task. So let me just step back and I think, say that obviously, if I just look at what are languages, let's all step back and say, what are languages? Languages are basically comprised of symbols. Symbols allow us to acquire, represent, share, and communicate knowledge, broadly speaking. Now, obviously, so that we can reason over that knowledge to generate new facts and guide our actions. That's basically, if I could combine all of this together and say that's the purpose of languages, to be able to, reason over the knowledge that symbols represent, and to generate new facts and to guide our actions. Now, languages have been fundamental symbolic systems through which humans have communicated. But there are languages of various kinds. I think some of the ones we obviously are most familiar with are human natural language, through which humans communicate with each other. But there is language of chemistry. I think we are all familiar with the periodic table. There's stories that are written as well, which is again to natural language. There's imagery. So there's choreography and imagery, which is combining more visual parts of the languages. And then finally, a language that all of us techies use all the time. It's the language of the code. And this is the one I'm going to more drill into in this particular task, which is language of how we define, how we spec software, how we reason about software, how do we implement software in machines, and how do we sort of verify software as well and test software. So that's basically where I will focus on and look at other parts maybe for a later talk. Obviously, we have seen the power of AI applied to human language. This is not a new topic. Again, that graph is a little bit dated, but I think the current wave of ChatGPT has taken the world by surprise. I think there isn't many even meetings at the government level now where somehow that topic is not interweaved in. I certainly was, it was interesting to observe at the World Economic Forum, that particular topic was the discussion of every day in every meeting on the implications of it for what might be happening in the world economy and in different tasks that can be potentially automated. Again, I think I want to be more careful as well, because we are very much at the beginning of this journey, and I don't think it'll surprise anyone to say, in the semiconductor world, as an example, that certainly part of this center is about, we are well familiar with 2x improvement of efficiency in every 2 years, or every 1.5 years to be precise, actually. That timeline has shifted a little bit as Murray's law has sort of plateaued, but every 1.5 years. If I just project similar level of performance to what will go on in AI, if there was an equivalent law, you would say if you are at a certain level of performance right now from efficiency and accuracy and capability point of view, in roughly speaking around 9 to 10 years, you will have 6 cranks of the you will have 6 turns of the crank in this particular case. So you are talking about roughly speaking 2 raised power 6. So you really are talking about almost a 2 order of magnitude improvement in where you are today to where you will end up a decade from now, assuming it follows that law that we have become all well familiar with. Whether the law happens because of performance improvements in hardware, software, algorithms, data sets, learning mechanisms, it'll be a combination of all of those. As I said earlier on, there are 3 legs of that stool, and all of them will improve. So, if we are mildly amused by what is happening with ChatGPT today, I think we should all be blown away in roughly a decade time, because we could expect slightly south of two orders of magnitude improvement in that performance. And that was sort of the hypothesis we had, that, okay, I think this is very interesting. And if you ask anybody, you say, what is we know natural language is the language of humans. What is the language of machines? I think all of us will say code is the language of machines. And just like AI has helped us master human language, we hypothesize that AI will help us master machine language as well. So things like language processing, basically symbolic processing applied to machine learning for software artifacts, automated reasoning and decision-making and planning technology applied to software artifacts, and explainable AI as well. Because the last thing, developers are a very I would say, skeptic bunch. So you need to explain things to them as well, like, why did you tell me that? Just because I told you so is not necessarily going to go down very well. So explainable AI really underpins a lot of this from almost a default point of view, because you need to explain your actions, or you need to be able to formally justify your actions as well. So just from the kind of task that we are looking at from an AI for code, we call this effort AI for code point of view. And several of my colleagues in not just within IBM, but across industry and various universities have been working towards almost a coalescing agenda around it on certain topics, which span from, I already talked about code language translation from legacy languages to more modern languages, code search and retrieval, which is on code discoverability, code similarity. I'm doing this task today. Can you find similar pieces of code? Code performance improvement in terms of even code debuggability as well, code memory improvement, which goes to code efficiency, and finally code classification, code explanation as well. What does this piece of code do, or what does this piece of code does? So that's basically all the gamut of various AI for code tasks we are looking at. This is not an exhaustive list, but we are looking at this quite exhaustively from a point of view of synthesis, first of all, generating the spec, to synthesis, to testing, to verification, traditional developer code development pipeline, and where can AI infused technologies be ingested as part of that DevSecOps pipeline, as we call it. Which actually resulted in, interestingly for us, this was a effort. As you look at what ImageNet did to the AI algorithmic development and the massive impact it had, we were looking at, is there an equivalent on the AI for code side? And we didn't find a exhaustive data set that was related to it. And we worked on something that we called Project CodeNet. There is a GitHub pointer right there. You can certainly go to it. It's a high quality code data set for algorithmic innovations and benchmarking. It's characterized by large scale, has around 14 million code samples, addresses around 4,000 plus code problems, has 55 different programming languages that are contained as part of it, has roughly around 500 million lines of code. It's a diverse set of problems and codes that are available. Codes are well tested. So there is a quality to that data set. We just didn't go and crawl the GitHub and put all of this together. We worked on gathering some data, curating that data as well, creating a set of problems. We have test and validation and training sets available, all highly curated. And we also provided, very different than other data sets that were available in this area, we provided test units, unit tests as part of it as well. So which could be used as part of your reinforcement learning mechanism, which is you have a prompt, which is a natural language prompt. You generate some code out of it. You actually can now measure the quality of that code because you know some of the good samples that exist. And then you can even, there are two levels of testing, I would say. One is, can you compile that code? That's first one. If you can compile that code, we also have test inputs available for you and the corresponding outputs so that you can measure, does the code, is the code able to do the task that we defined it for it to do? Not just you can compile the natural language prompt into a code and compile it, but does it do the task that you want it to do as well, which can be measured by the test data, which is provided for each of the problem as well. So again, you and some of your students or your colleagues can certainly go and look at this. This has been gathering more and more steam lately. as the area becomes more and more of active interest by the community in terms of AI, to be able to address various tasks of the coding sort of development process or code development process. In particular, we also release some models as well as part of it for like code similarity and others, in terms of graph neural network based models and others, which are part of the CodeNet project as well. And we continue to release more and more capabilities. So just recently, actually 2 weeks back, almost 10 days back, we announced something called Minerva, which is part of taking AI to be able to, as part of Project CodeNet. So Minerva is part of the Project CodeNet, for AI to be able to analyze and refactor code as well. So we call it sort of from a monolithic code to a microservices-based code as well. So that's also part of our overall effort on Project CodeNet, and for AI for code, broadly speaking, a open source effort that we have. As I said earlier, this is the largest AI for code open source data set available today, accelerating the intersection of AI and software, broadly speaking. And obviously, our goal is to take some of the more fundamental language understanding technologies that we have applied to master human language to help us master machine language in sort of 3 domains that I already talked about. Now, obviously, I think all of us will say code is the language of machines, but there are interesting parallels and some interesting differences between 2 of them as well. I think the parallels are, if I just look at the polyglot dimension of languages, just like in human languages, we have English, Spanish, German, Mandarin, Hindi, others. In machine languages, we have polyglot of languages too: Java, Python, COBOL, C++, PL1, you name it, actually, Fortran. They all exist as well. In terms of the vocabulary, we've got in human language, we've got words, nouns, pronouns. In machines, we've got variables, functions, classes. Now, obviously, the syntax is much more tighter. So that's basically one of the differences. You have obviously comma, full stops, exclamation marks, so on. And we have similar kind of syntax, obviously, mechanisms in machine language as well. But I think there is a significant difference, and people will typically say, shouldn't coding with AI be much easier? And I would say yes and no. Yes, being that, yes, you can certainly, obviously there's well-defined syntax and you can produce it. But I think no, in terms of in coding, either you are right or you are wrong. There's no kind of right, actually. You were given certain inputs, you produce certain outputs. You may be able to compile the code, but it may not do exactly what you want. In human languages, there is a sort of a variability. And I know what you mean. There is no such thing as I know what you mean in code. I mean, either you are right or you are wrong, because the machine is going to execute on it, and you need to be a lot more stringent in terms of the quality of the spec that you are expecting, because the spec is not just behavioral, it's also executable as well. And it has implications on many of the processes, business processes and other processes that we have gotten used to. So it's easier in some ways, and it's much harder in other ways, because the quality that you need to produce is much higher as well. And obviously you need to understand the context for language understanding, because obviously machine code or programming is spread over a significantly larger array of files. It can go into millions of lines of code, sometimes tens of millions of lines of code as well, single application. So it can become quite complex from a context point of view. We've been working towards this from a very systematic point of view as well. We have obviously, at the bottom is what I'll describe as our data layer, which is a code repository. When we talk about data in coding, we are not just talking about source code. We are talking about code repositories. They could be actually both static source code or even compiled code as well, so object code too. We have logs, we have test suites, we have dialogues between developers, we have other application docs, we have deployment code, which is configuration. So think of it as infrastructure as code. I just talked about configuration. We have data models, all kind of repositories that go into this. The layer in yellow that I'm showing is our, what I'll say as our data ingestion layer and data integration layer, which is source repo analysis, masking and redaction, data labeling, data curation, code and text data sets are, that's where code and text data sets appear. In fact, interestingly, for anyone who is who either is doing this as part of what they're doing today or plans to do it, this is where significant effort goes in the beginning on getting the right data set. Even if you are crawling this off GitHub, making sure that your licenses are okay and all of that work, and kind of getting the data in the shape so that you can start ingesting it as part of the layers I'll talk above as well. Then we have obviously, one thing that is kind of missing from human languages is in machine languages or in coding, we have something called intermediate representations. When you have compilers, they take a high-level machine language or a high-level programming language, they compile it into what is known as intermediate representation, also called as IR. Compilers like LLVM and others take that and compile into intermediate representations. And we can do some formal analysis on those intermediate representations. So this is, again, where one of the major differences lies between machine language and human language. We have 3 decades of knowledge built upon, or no, I would say almost 5 decades of knowledge at this point, built upon analyzing and synthesizing programming languages. Obviously they have underlying computation and flow mechanisms with control data flow graphs that reside in there. Grady and team have done some phenomenal work on formalism of many of those languages as well as how you represent certain tasks from abstractions point of view. So that's the reason I'm highlighting this a whole lot, is that you can use the traditional part of how we represented programming languages and symbols to mix this with language understanding technology more recently. So currently, most of the technology that exists for, interestingly, large language model, to a large extent, it is a token prediction technology. It works beautifully. I totally agree with it, but to a large extent, even the AI for code things that you are seeing as part of ChatGPT, they are not yet integrating tremendous amount of capabilities that have been developed over the last 3 years into how they are predicting those tokens. Because they are predicting it as just part of, hey, this is yet another language. Well, yes, it is yet another language, but it is more than yet another language, because there's a formal mechanism that goes behind it. And this is exactly where we are focused on, in combining the formal representation of the languages, the formal analysis we can do, bringing some rule-based systems as well, combining it with the LLM technology to bring together what we will call NLP-inspired large foundation models from a code and text embedding and transformer models point of view, to combine them with intermediate representation-based analysis, rule-based models, static analyzers, to really give rise to what we call task-specific AI models, which is, again, part of our overall effort around CodeNet. And more recently, we have released it as part of a joint Red Hat IBM project called Project Wisdom, which is exactly about generating code for, in this particular case, a certain task of code for IT operations. How do you define infrastructure? How do you manage infrastructure? All of that is done in a language called YAML, funnily called, sort of in a fun way called yet another markup language. But again, that's language of the IT developer, that's how IT developers interact with the infrastructure as code. And all of this is really, if I could say 4 things we are doing from a capabilities point of view. We are building capabilities to understand language, coding as a language, to be able to review the code, to be able to retrieve and generate the code, and to be able to test and verify the code. And the layer at the top that I'm showing in kind of maroonish color is a application layer. We are building applications with all these capabilities and the data and the AI for code stack that I'm showing below it, for app vulnerability analysis, for app modernization. I talked about refactoring and building microservices, for app development, for app operations. Project Wisdom fits right in there as well, for app testing, and for compliance and other things as well. Again, these are some of the massive applications that every enterprise builds and relies on a regular basis. All of this in a sort of underpinned with this or on the side with the explainable AI, whose need I motivated earlier as well. So I think just I wanted to move now to a topic which obviously is of critical importance, and I know I'm sort of running out of time as well, and I want to take some question and answer. So I'm going to reserve roughly around sort of 7 to 10 minutes as part of it. So I have roughly 10 minutes or 12 minutes to go to be able to cover rest of the things that I wanted to at least have a discussion on here. I think it'll be fair to say, and this was a chart pre-ChatGPT era, and I think many of you, in particular Grady, who knows me, I've been on this topic way before any of this was popular. I felt very strongly about it, that this was going to happen, and it is happening. I believe we are nearing an inflection point in AI, triggered by self-supervision at scale. And what's next in AI is really pre-train in an unsupervised way and then adapt. The generalization capabilities of these models is becoming just phenomenal. And what is now known as emergent properties, which properties emerge out of that training that you may not have designed that particular network for, which is the most interesting aspect of what we are witnessing today. And a lot is not yet known about how all of that is happening, but certainly a very interesting phenomenon is emerging. I think the story of AI, I would really say, if I just go back and look at it in last 4 decades or so, it's what I'll describe as story of data representations. If we go back in 80s, obviously there were expert systems, there were handcrafted symbolic representations. You move forward from late 80s to 2010s. You start looking at machine learning systems, which are task-specific, handcrafted feature representations. It took a lot of effort, a lot of subject matter experts who understood the problem, who understood what features were important to that problem, and modeled those features for methods like SVMs, decision trees. Neural networks are part of it, and random forest, and a whole bunch of other methods. But feature design was a critical part of that. And using some of the, obviously algorithms emerged to help in that domain as well. Now, if you look at sort of starting in early 2010s, obviously there was a re-emergence of neural networks as part of very deep networks with deep learning. We talked about this enough as well. And more recently, we are in the era of what I'll describe as foundation models, which are generalizable, adaptable, learned representations, self-supervision at scale, massive data, and compute. So if you look at sort of transitioning from the 80s era into kind of late 90s and 2010s, it was the era of big data. Then it was early 2010s to now massive big data and massively large compute. And then more recently, in last 3-4 years, it's self-supervision at scale that got added to it, with massively large data and massively large compute, giving rise to what I sort of everyone terms as foundation models. I think this is, again, just on the left side, the chart is important because some of these models are becoming massively large, actually, overall. And I won't harp on it too much, but again, I firmly believe we are once in a decade opportunity where huge foundation models are turbocharging AI progress. And I'll talk about the huge part of it because I take a contrarian view on it, actually. And we've been driving more on the efficiency part than on beating your chest on I have 1 trillion model and I have a 10 trillion parameter model. we actually in IBM, and I think our colleagues as well, have been blessed to have some of these very massive infrastructure. We have thousands of A100 NVIDIA GPUs that we are working with. I think I just briefly talked about this in terms of Project Wisdom, and we have picked an area which is important to us, as a hybrid cloud company, and which are at the intersection of, IBM strategy is hybrid cloud and AI. We actually sort of been using this cluster to help our, the community, the Red Hat developers, which is as all of you know, Red Hat is an open source company built on open source software, but also one of the key players in open source movement as well. And I think I was talking to you earlier as well. In the chip design era, we are much behind in embracing open source. We have effectively, I should say, we have two companies which have monopoly on our flow, having lived that tool chain very, very well. I certainly know it. So we need to go and really look into open source software and implication for it for sort of chip design domain as well. And that's the purpose of the workshop that we are having in sort of early March as well. So Project Wisdom is really about bringing the power of AI to a IT sort of IT operations, IT developer in terms of their language is what is known as YAML, which is, by the way, language used by roughly speaking 500,000 developers around the world. Just to give you a context, total number of developers in the world are roughly around 25 million. So it's part of a significant section of that population. The goal for the Project Wisdom has been to address the skills gap for IT automation to help the developers be more productive and reduce errors. We are driving this with really quality at its core. The data set that we've been using is a highly curated, highly governed data as well, which Red Hat obviously governs from a community point of view for Ansible community, which is much larger. The goal is quality at its core, faster, scalable, and efficient. And there are two things I will add to it, which I have captured in another version of this chart, which I think are very relevant to the discussion here. If you talk to the enterprises, I think they will say, and I'll explain the right-hand bar graph as well as part of it, but if you talk to the enterprises, they'll say, what are things that are important to you? I think consistency will be a critical part of it. Let's say you and I, somebody in my listeners who are sitting there and I are sitting there on a table, we type the same prompt to the model. It's likely we'll get different responses back. Now, that may be okay in a non-enterprise context. That can become a problem in an enterprise context where large team of software developers are developing the software. It's not just one individual or one graduate student who is developing software. Literally, many times hundreds and sometimes thousands of people are involved in developing these complex applications. And consistency of task is very important. You may be lower in quality. That may be acceptable because we can recover that quality somewhere else. But you must be consistent. Inconsistency is bad from a process management point of view and software developer efficiency point of view. So that's another one that I just wanted to add. And we are right in the middle of some of the more fundamental research on what does it mean to be consistent in software? How do you measure that consistency? What are the metrics for it? What are the data sets that will go into defining that? And the second part, which I believe is even more relevant, is many of you are aware, Microsoft is in a lawsuit currently between the community and Microsoft on the legality of Copilot. All of that will play out in the court, so I'm going to keep that aside. But what I'll describe as attribution. If you are somehow a model, a large language model, just picked up a snippet from somewhere which happened to be written by Ruchir, let's say, in the community, please acknowledge it. Because if you are copying, then please acknowledge that you are copying. Yes, I have given you licenses and so on, but acknowledgement is important to this community. And one thing that we are focused on quite a bit on is attribution, which is the differentiating part of wisdom. So wisdom is about customization to an enterprise. Many of the enterprises, almost all of them, have their own data, which resides many times in maybe it resides in Azure, AWS, or in their on-prem data centers, wherever most of their development is being done. We need to take these capabilities to them on their data. They have certain standards, they have certain best practices, they have their own applications for IT automation. It's about customization, it's about high quality, and it's also about efficiency of delivery, and which is what I'm pointing out on the right-hand side. If number of parameters, which they are a proxy to deployment efficiency, the Copilot and Codex that many of you will be familiar with, the model number of parameters are 12 billion. The number of parameters in Wisdom model, which is a large language model again, as well, are 350 million. That's more than 35x better. And interestingly, Blue Score is a standard metrics, which is acceptable, invented by IBM Research as well, which is accepted across the board as a standard metric for measuring language accuracy. We are much better in accuracy. So we are 35x better in sort of efficiency or size. We are much better in terms of the quality as well. And then we are also better in what we describe as task-specific metric, also called as key score. So overall, I think our goal is, and the why is that size important. All of this is being delivered with software as a service, also known as SaaS. In SaaS, APIs that all of you would have consumed in one way or the other from some provider go by literally either they are on free plan or they are what I describe it as pennies by pound of APIs. So delivery efficiency in terms of my infrastructure cost is critically important. I think Sam from OpenAI is on record saying, if you see at the cost of delivering ChatGPT, your eyes will water. The costs are so high. I mean, they will figure out their monetization mechanism. It's their business model. But what I'm trying to emphasize is, if I needed A100 to infer on these models, just to give you a cost sort of idea, if some of the A100s in kind of spec we need in AWS instances cost roughly around $30 an hour. If I'm using a much smaller or much less powerful GPU like V100, NVIDIA V100 GPU, that's like $3.50 an hour. If I'm using CPUs, you're talking about south of $1 an hour. So you're looking at sort of really a range of 35x or 40x range in terms of cost. So if you are 35 times smaller, then potentially you could even infer it on a CPU. It will depend on the latency of the use case and so on. But our goal is to go smaller and be more efficient, focus on single tasks. I'm not interested in doing 1,000 tasks that ChatGPT can do. I want to do one task and one task well, because that's what enterprises are interested in. And we are leveraging that to basically look at this from an efficiency point of view. How do I use that particular criteria to make my language models much better for software? Again, I don't have time to go through this demo. You can go on Google, look for Wisdom. We have keynotes in there that I had given in October. There's demos in there as well. So I won't waste sort of a lot of time on this. So just, I think one thing that demo actually that unfortunately I don't have time to go into as much is, so the person who actually is the voice, whose it is on that demo, Matt Jones, he's the chief architect of in Red Hat, sort of architecting a lot of Ansible. He actually said that demo, it would have taken him an hour to do. And he's an expert at this. The machine was able to do this in, he said, couple of minutes. So give and take 5 minutes. You are looking at an order of magnitude improvement for that task. I'm not saying that's all he does in his day. For that task, for code development. And he also said it'll result in more standard practices being enforced. because the model can now start enforcing certain standards and best practices in the development community within an enterprise as well. So it has many benefits to it, not just about development efficiency and productivity of a developer, which can be an order of magnitude, but has implications on code quality, code and other metrics as well. Again, I think just to summarize, we are looking at this from a broad point of view, from code generation to code search and retrieval to code language translation, code performance improvement. And again, we have a lot of effort going on in this area overall. I'm just going to stop there in the spirit of really taking questions and happy to again take questions on it, address anything you want me to address, and take it from there. I just want to keep a couple of minutes for us to talk about this more broadly.
Thank you. Yeah, questions.
Okay, can I start? So this is Igor Markov. Hi, Ruchir.
Hey, Igor, nice to see you.
Yeah, great talk. So I have 3 questions ranging from fairly technical to research strategy. I'll kind of ask them, and feel free to answer any subset of them. The first one follows on your kind of most recent segment, the latest segment. You mentioned the example with increased productivity. So I was wondering if there are good metrics for how AI assistants help, coders, programmers, in terms of writing industry software, not for just specific tasks, but kind of bulk metrics, right? Do you want me to go through all the questions and then you can answer, or do you want one by one?
Yeah, why don't I think that's certainly a very important and a meta question. So I think let me take that one first, and then we can decide, Igor. I'll tell you what we are doing, and that may or may not be perfect. So what we are doing is we are looking at it from multiple points of view. When we roll out a capability like this, so I'll tell you, we have a pilot going on in our CIO team. We have roughly around 10,000 developers in our CIO team. IBM is a large company, as many of you know. We have a lot of developers in CIO team. So we have a pilot going on where we have decided 3 levels of skills: beginners, intermediate, and advanced. We rolled out the pilot to them, and we are actually measuring productivity on certain tasks. First of all, it's more at a task level. Then we are looking into overall, they spend their time on many things, including problem definition, debug, many times just addressing questions. Look, what impact it has on an overall developer productivity, because that's not the only task they do. It's easy for us to claim 10x and feel happy about it, but if you only improved it 3% of the thing, then of course we should be honest about it as well. So that's the other one we are measuring. The third thing we are measuring is, and I'm not very sure that's directly what you were asking as well, is what I'll describe as our NPS score, satisfaction. Did you help me, or really, I knew all this before as well. I could have done this in maybe a couple of minutes in any case. You are techies, you want to feel good about it, but I really didn't make much of a difference in my life. So that's more of a subjective one, which we'll describe as an NPS score of developer sentiment. If I may call it a sentiment, that's developer sentiment. Did you make difference in it or not? So we are measuring it at 3 levels: task level, broader developer productivity level, and then what I'll describe as a sentiment level, all 3 actually. Does that make sense?
Yeah. That's good. So, yeah. So
we, in the interest of time, could we first let another person ask another?
Oh, sure. Question? Yeah, that's fine.
And we go back to you. Sorry.
Go ahead.
No. You want to unmute and ask? Okay, never mind. Igor, please go on.
Yeah, so the next question is kind of broader: language versus reasoning. You emphasized many things that are specific to language, expressing new claims or facts, and programming. But some of the kind of debates, especially related to ChatGPT and applications like this, are about these language models being great with language, but not being great with reasoning, and having no idea about what truth is, right? So in programming, we can test the program, we can know if it runs, right? How do we combine these things, and what's kind of next in terms of research?
So this is, I think, where Igor, I believe we have a, if I may say, leg up actually on, there's syntax part of it, and there is, semantic part of it, which is where reasoning comes in. The world in which we live in coding, has sort of semantics very formally captured. It does certain tasks, it has a controlled data flow graph, it has an intermediate representation. And that's the point I was alluding to when I said intermediate representations. And we can have, Igor, a discussion on the side. That's a much longer topic on how we are doing it. And that's why, as part of CodeNet, we had rolled out tests as well as part of it, because now you can start using it as, you can execute the snippet, which is, again, it's a part of reasoning built in because it has a behavior. You can execute that behavior, see how you close you are to a certain sort of target as well. And also we are combining, this is more in the translation scenario, we are trying to come up with a more unified semantics through which, or an intermediate representation through which we can do end-by-end translation across languages. Again, more detailed and nuanced topic, but that's exactly where I say languages, specifically coding and machine languages, have an advantage because the semantics are very formally captured.
Great. Okay, Mikhail, do you have one last question that you want to ask, and we wrap up after that? You're muted. Mikhail, please go ahead. Yeah.
Okay. Yeah. Thanks. Very nice talk. I really enjoyed it. I have a question. I mean, it's so we have seen this amazing, rise of neural networks over the last 10 years or so, right, since AlexNet. I guess my question is, there is no guarantee that neural networks will continue to be the best models in the future, right? It's certainly historically we have seen that different methods have become popular and sort of showed state of their performance. What happens, I guess, what's your view? Or like, what happens if maybe in 10 years there will be some sort of different set of methods? How would that affect sort of the future of software and AI? What are your thoughts about that?
I think nobody can, if I could predict the future, that would be a different thing. Obviously, I can't predict the future. Having said that, I definitely believe this is one of the key elements of technologies we will build upon, at least for the foreseeable future. Now, it's possible something else comes along totally. This will not be the only element. That also I'm convinced as well. For anybody says this is the nirvana, this is not the nirvana. I think, Igor, you already referred to some of the reasoning parts. A lot of debates going on between Jan and other people on, obviously, and he's absolutely right. That fact is very well utilized. But I'm being more practical on this. This is amazing technology. And I believe for next 5 to 10 years, this is something what we will build upon in industry from a practical applications point of view. Because technologies like this, there's large investments that go into it. Companies expect return on investment. So it's, even if an academic technology came along, it takes a long time for it to get into the entire system and people to pivot as well. That's why I'm saying there is a dampening factor to, it doesn't happen overnight. And I think this is such a large step function in where we are from an abstraction level point of view. And another thing, Michal, I wanted to point out, I didn't yet talk about in this talk, and this is another one that I've been mulling around on, is I believe, I think all of us as computer scientists know the name of the game in computer science has always been abstractions. From punch cards to assembly to Fortran to C to C++ to Java to, you name it. It's a step function in abstraction. That doesn't mean to say other abstractions go away. Now, new formalism have to emerge in terms of how do you combine these different levels of abstractions. And I think programming language, sort of PLSE community is almost caught off guard with this in some ways, I would say. Like, it hasn't just settled in yet regarding this is a significant sort of improvement or sort of higher level of abstraction. that's emerging, and it has to be matched by the rigor that the programming languages community is used to in terms of abstraction levels. And we are not there yet. Actually, at least from what I have observed, the community is caught off guard with how fast things have moved. So just to answer you more directly, I believe in next decade, this will be the workhorse we will ride, actually. Would somebody else emerge after that? Well, I would be surprised if it doesn't, actually. I'm sure it will, and I hope it does, actually. But to me, it's a decade-long journey, and it'll run its course till end of 2030s, actually, at least.
Thank you.
Thank you so much. I guess we'll wrap up now. This is a bit over time. So thank you again, Ruchir, for talking to us. And we'll have more in the future.
I appreciate it. This was a fun discussion. Many of you know me, so reach out as well. I'm sure we'll bump into each other in some conference as well. So it was great. Thank you.
Thank you. Bye.
Appreciate it.